In this video, we present Sat2Scene, 3D urban scene generation from satellite images with diffusion, which aims to overcome the challenges of direct 3D urban scene generation. For a single satellite image, we utilize 3D sparse diffusion models to generate 3D scene textures for the predicted geometry, which can be transformed into scene representations used for rendering either ground view or bird view videos with robust multi-view consistency. The motivation for our approach includes two key aspects. On the one hand, generating in 3D space instead of 2D space ensures consistency when rendering to 2D, providing temporal consistency across frames, loop closure for long-term consistency, and even consistency across different videos. Also, it naturally maintains perspective photography and eliminates the need for preset trajectories. On the other hand, using diffusion models offers superior performance compared to GANs, ensures a stable training process, and does not require a discriminator, thus avoiding the need for on-the-fly 2D rendering. The input of our pipeline is the geometry of a scene, which can be either inferred from a satellite image, using the estimated building footprints and height maps, or directly provided by the user. Evenly distributed points are sampled from the geometry and initialized with random noises, which are further passed to the 3D denoising network with a sparse setting, resulting in a colorized point cloud. Meanwhile, a 2D latent diffusion model is adopted to generate the panoramic scene background. In the rendering phase, the denoised point cloud with preliminary color is first passed to the associated feature extractor to obtain the point-anchored scene representations. Finally, a neural renderer aggregates the necessary information from the neighboring points' representations along the rendering rays and produces images for arbitrary views. The generation part and rendering part are trained separately and are integrated during the inference phase. We perform experiments on Holy City and Omnicity datasets and compare our model to state-of-the-art methods, Sat2Vid, Infinicity, and MV Diffusion, on a wide variety of evaluation metrics including a user study. The quantitative comparison on the Holy City dataset with the baselines demonstrates our superiority in overall video quality and temporal consistency with the on-par single-frame generation, and ours are more recognized and liked by the users. The qualitative comparison on the same dataset shows that ours generates more plausible videos with better multi-view consistency. In addition, we make an ablation study in a leave-one-out manner, removing the individual component from the final pipeline to better evaluate the effectiveness of these factors. The quantitative results show that each component brings gains to the final model. The qualitative results show that the 3D sparse diffusion model may not work on a point cloud with unbalanced density. The point aggregation and the depth supervision also make the rendering clearer and better fill the holes. Generalization of our pipeline to the Omnicity dataset for the satellite-to-ground synthesis task also demonstrates the usability. Ours consistently produces frames with superior consistency across different positions and view angles. In contrast, MV Diffusion generates videos with varied textures across frames. To conclude, we propose a novel diffusion-based framework for direct 3D urban scene generation from satellite imagery. It brings diffusion models into 3D sparse representations, generates scene features tightly associated with the geometry, and integrates with neural rendering techniques for rendering arbitrary views. As a takeaway point, we found that diffusion models learn better on the 3D point cloud with a balanced point density. We believe that our work is a step forward in 3D scene generation, offering a promising avenue for the development of 3D generative models. Thanks for watching. Please find more details on our paper and project page.